so I just did a little back of the envelope calculation. If you could do 1,000 iterations per second on your computer, doing these 70 by 70 pivots, this problem would take 40 billion years to solve. And the age of the universe is about 13.7 billion years. So that's a problem if you can't do anything bigger than 70. Yet problems with 10,000, 100,000, even 1 million variables are solved routinely, actually. Even on this computer, I solve problems routinely of the size of hundreds of thousands. So this is a worst case, and so you can see that computer scientists and theoreticians love the worst case analysis because it's mathematics. It's rigorous. But in this realm, it just doesn't tell you much about the problems in reality. By the way, I want to just say one last thing about the Complementary problem. In all of these cases, in all of the Complementary problems, you can get from the initial dictionary to the optimal solution in one pivot. If only I had picked the opposite variable at the other end and done it, we would have gotten there in just one pivot. So that also shows that the different heuristics for how you pick your entering variable can really make a huge difference. But nobody really knows a foolproof way to get a good entering variable rule. Okay, brief summary of complexity. Quadratic isn't bad. Cubic's worse, but not terrible. Exponential is terrible. As I think probably everybody here knows, fast sorting algorithms are n log n. Simple but slow ones are n squared. Matrix times a vector is an n squared type algorithm. Matrix times a matrix is an n cubed type algorithm. Matrix inversion is n cubed. So the simplex method, in the worst case, is 2 to the n pivots and n squared operations per pivot. And so it's n squared 2 to the n operations. That's the worst case. But empirically, and I'm going to show you about this in just a minute, the average case is vastly better. It's just n cubed, roughly. And there's there's algorithms that are not the simplex method, and I'm going to show you one at the end of this course that achieve this also in the worst case, but it's not the simplex method. That doesn't achieve exactly end of the 3, but close to it. And so there's an open question. Become famous. If you can give a variant of the simplex method whose worst case performance is provably polynomial. There's lots of choice. You get to pick your entering and leaving variable, your pivot rules. If you could come up with a pivot rule that you could prove is polynomial, you'd be instantly very famous. So roughly speaking, the best algorithm is n to the 3.5 operations. And I'll talk a little bit about those kinds of other algorithms at the end of this course. So let me spend a few minutes now talking about the average performance. I did some simulations just a month or 2 ago. And so here's some code, actually. MATLAB program that implements the simplex method. So I generated random m and n. I wanted it to be distributed from 1 to 400, but I wanted it to be uniform on a logarithmic scale. So here's how you do that. I then generate a random matrix A with normal random variables. So these are normal 0, 1 random variables, and I multiplied them by some sigma just to give them some spread, some standard deviation. Did the same with the right-hand side. Then I chose C in such a way to guarantee that there was an optimal solution here. I'll talk about, I haven't talked about the ideas that explain this, so I'll skip that for now. Anyway, here's the entire code. While we're not optimal, pick the largest coefficient. So there's the MATLAB code for that. Select the leaving variable. Here's the MATLAB code for that. So I've got the col is my entering column, and row is my leaving row, and a col is the column of the matrix associated with that column. A row is the row of the matrix associated with that column. A is just that entry at the intersection of that row and column. That's called the pivot element, by the way. And here's the code for one pivot of the simplex method. You have to update the A matrix, you have to update the right-hand side vector, and you have to update the coefficients in the objective function. So just update A, B, and C, and that's the entire simplex method on a page. There you go. So I ran it over and over and over again. This was 1,000 or 2,000, I forget exactly. So this is how many pivots the simplex method took as a function of m plus n. And actually, I've been doing optimization for 20 years now, and I'd never done this until just a month or so ago, and I was at first surprised by this picture. I expected it to follow some kind of curve along here of some shape or something or another, and I was surprised to see all this stuff over here. I was puzzled for a while, but eventually I realized that actually that makes some sense. Because some problems of size m plus n are much easier, take much fewer pivots than you might expect. And it's kind of easy to think about once you start thinking about it, what that would be. And I think the answer is, if m plus n is equal to 100, because n was 95 and m was 5, so that your problem just had 5 constraints and 95 variables, that's probably fundamentally easier than if it were 50 by 50. Similarly, if it had just 5 variables and 95 constraints, that's probably also fundamentally easier. In fact, maybe that's the easiest thing to say. Suppose I had m plus n equals 100, but I got that with just 2 variables and 98 constraints. And I'm generating these things randomly. So now I can do this, I can plot it. I get to write 98 of these things down. 98 of them, and then it's the intersection of all these. Now I chose those few lines of code that I didn't explain to you in such a way that I know that there's a feasible solution. So the intersection of all these things is not the empty set, it's something here, let's say this. Well, you can see, even though I've drawn 98 half planes, my polygon that I just drew here only has 4 vertices. So it's probably very easy to solve. So I think when either m or n is small and the other one is large, it's probably fundamentally much easier than when they're both about the same size. And so my little experiment was interesting to me. I'd never realized that it makes a big difference. And so then I plotted it differently. I plotted it against the minimum of m and n to see, since that seemed to be the more relevant measure. If the minimum is small, then it's an easy problem. And so let's say it's a small problem anyway. So plotting with m min n, now it looks like I've really captured what's going on here. And so I plotted these points and I did a regression here, and I get that it's approximately, the number of iterations is approximately 2/3 times the minimum of m and n raised to the 4/3 power. Now whether these 2/3 and 4/3 are actually fundamentally the truth, I don't know. It seems kind of compelling because 0.68 or 0.69 seems pretty close to 2/3. 1.3347, I don't know, maybe, is that just luck? I only did this experiment once, but I did it with a couple thousand points. I don't know. Open question. If that's a true theorem, that's very interesting, but I don't know. Here I just plotted it on a, rather than a logarithmic plot, I plotted it on it linearly so that you can see that it does look like it's a not power 1. It does look like it's growing with some power higher than 1, such as 4/3 here. So you can this was important to me because I actually thought that this power here was going to be 1. And so the fact that it's a little bit more than 1 surprises me. But it looks like it, at least in the way I've generated these random problems, it looks like it's real. And I think the way I generate the random problems is fairly legitimate. Okay, oh, I also made an ample model, which maybe in interest of time I will skip. This is code in this other language that I like that does the same thing. And it also fits on 2 pages, so it's not too bad. And you can download the ample code if you like. All right, now, enough of worst case and average case analysis of the simplex method for the time being. Let's talk about another topic that's really of fundamental importance. Duality theory. And this is really why linear programming is a fundamentally important, well, okay, there's 2 reasons why linear programming is fundamentally important. One, there's lots of real-world examples, and I'll describe some to you later. So from a practical point of view, lots of examples. But mathematicians, theorists are also interested in linear programming because there's some very fundamental ideas here, and it's called duality. And so, and this is going to tell us a lot. It's going to inform our newer versions of the simplex method. It's going to inform us on how to derive other variants and get us to that end of the 3.5 algorithm. Okay, so every problem has a dual. This is our primal problem in standard form. The dual is a minimization problem. The right-hand side becomes the objective coefficients. The objective coefficients in the primal become the right-hand side. The constraint matrix A gets transposed. So where here I had M constraints and N variables, here I have N constraints and M variables. We just introduce another dummy letter, Y, for the dual variables. So here it is. It looks very much like this, except for it's greater than or equal to constraints, and it's a minimization. But other than that, it looks very much like the primal problem. In fact, the fact that these two look very much alike is really why I prefer to start with problems in this form, which is that in this decision I diverge from many other standard textbooks. But I think the reason is that there's a beautiful symmetry when you do it this way. So the original problem is called the primal problem. A problem is defined by its data, and so we just have an A, B, and C that really define the problem, and then the dual problem has the same data, well, but used in a different way. And actually, if we write the dual problem in our standard form, so I convert the minimize to a maximize, how do I do that? If you want to minimize a function, we'll just take its negative and then maximize it. And then when you're done, negate that again. So I maximize minus B transpose Y, and then I just have to negate my answer. Similarly, I want less than or equal to constraints to be in standard form. How do I do that? Well, I just multiply both sides of this inequality by -1, and I get it like this. So now we see that oh, a typo. I've never noticed this typo. There's supposed to be a transpose on the A matrix right there. So the dual problem is simply the negative transpose of the primal problem. In fact, if you look in the dictionary, right, it really looks like the negative transpose because the C is here and the B is here and the A is, oh sorry, in the original one, the B is here, the C is here, and the A is here. And if you think of that as just one big matrix and take its transpose, the B and the C get switched and the A gets transposed and everything is exactly right. So this really is exactly the negative transpose of the primal. And so the first theorem, which is such a trivial theorem I don't even write the word proof down next to it, is that the dual of the dual is just the primal. So, and that's why it's called the dual. The dual of the dual is something else, we would call it something else. And so the first theorem is that the dual of the dual of the primal is trivial. The second theorem is also very simple and fundamentally important. If we have values of x that are feasible for the primal problem, and somebody gives us values of y that are feasible for the dual problem, then the current objective function for the primal, C transpose those values of x, will be less than or equal to B transpose y. The feasible primal objective values are smaller than feasible dual objective values. And the proof is really trivial. You don't even have to remember it. All you have to remember is start here. Write down y transpose AX. And then use the two assumptions. X is feasible, y is feasible. So let's try to do that. Let's see here. Let's take the y transpose A. That's a row vector being multiplied by a column vector x. Let's take that row vector and write it as a column vector transpose to make it a row vector, so that y transpose A is A transpose y transpose, right? But the dual problem, A transpose y is greater than or equal to C. That's part of dual feasibility. And part of primal feasibility is that all the numbers x are greater than or equal to 0. So this is a sum. We're summing up elements of this vector multiplied by elements of this vector. These things are all non-negative. And so if I can put smaller values in for these, I make the whole sum smaller. And smaller values are the coefficients in C because of this inequality. So C transpose x is less than or equal to y transpose AX. We're doing exactly the same thing on the other side of this equality. We just say, look, okay, I can rewrite y transpose AX as AX transpose y. That's obvious. But AX is less than or equal to B. That's part of the primal feasibility. So it's the same idea all over again. We've got this is less than or equal to something, and all these things are non-negative. Therefore, the whole sum is less than or equal to those coefficients times these y's. So it's completely trivial. We've used all of the conditions of feasibility. We've used all the conditions of primal feasibility here and here. We've used all the conditions for dual feasibility here and here. So we haven't underused or overused anything. We've used everything exactly once, and we get this nice result that the primal objective must be smaller than or equal to the dual objective. So we can look at this on a plot, on just a real line. We just plot objective function values. If I plot the primal values in purple here, it gives me some interval of values. This interval might extend to minus infinity. And if we plot the dual values, we get another interval, which I've shown in green, which could extend to plus infinity. But all the green values must be bigger than all the purple values. And one of the fundamental questions is there a gap? Is this possible or not? Or is the situation always like this? This would be a nice theorem if you could prove that there's never a gap between the primal and the dual. The answer to this question will come from the strong duality theorem, which we'll have shortly. And it's not quite trivial. Okay. Now let's think about our primal simplex method in the context of the dual problem. So we have a primal problem. Here it is. I write down its dual. So I have a little pivot tool version which uses dual notation. So I've got y's here. I've got z's. Oh, so on the dual side, I always use z for the dual slacks and the inequalities. So in the primal, I always have x's and w's. In the dual, I always have y's and z's. And the dual is exactly the negative transpose. So the minus 3, 2, 1 become a 3, minus 2, minus 1. The 0, 3 becomes a 0, minus 3. And this matrix, this 2 by 3 matrix, becomes this 3 by 2 matrix, which is the negative transpose. Now, let's do the simplex method on the primal problem. We're feasible, so I can do the primal simplex method and see what happens. And let's watch what happens to the dual problem. So I pick x2, it will be my entering variable. And W2 has to be my leading variable. It's actually my only choice in this case. And let's see what happens. So after I do the pivot, here's the new primal dictionary. Here's the coefficients. Now, if I do exactly the analogous pivot in the dual problem, so I clicked on the middle column and the last row. If I click on the last column and the middle row, that's this Y2 over here, that's this button here is the transposed slot corresponding to this X2 button here. In other words, there's the 4 here, there's the -4 here. This button corresponds to that button. If I click on this button, I can do the algebra. It doesn't look like the simplex method because I'm not even feasible. Nothing I said before makes any sense for clicking on this button. But I can do it. I can do the algebra. I can rearrange these equations and see what I get. So I'm going to click on that button there and this button here, and what I get is this. So I've done a legitimate primal simplex pivot on the primal problem and improved my objective function from 0 to 3/2. I did the corresponding pivot on the dual, which was not motivated by anything other than being analogous to what I was doing on the primal. And look what the beautiful thing that's just happened here. I still have the negative transpose property. -3/2, -3/4, -3/4, 3/2, 3/4, 3/4. Every row here is the negative of every corresponding column here. The negative transpose property is preserved under doing the analogous pivots. This is a very important fact. And even though I'm not writing down a proof, it's a trivial proof. You just have to look at those few lines of my MATLAB code, understand exactly what's happening in a pivot, and show that you have this property. So we do the second pivot here. Oops, I should have said this. We do the second pivot, so X3 will enter. Oh, I have to do a few ratios here. This is 3 going at a rate of 9, 3 going at a rate of 1, the 9. So W1 must be my leading variable. I guess I said that down here. So the 9/4 is the number to key on. So I look for the 9/4, the negative 9/4 down here. So I click on this button and I click on that button and I compare. And I still have the negative transpose property. So now this dictionary here is optimal. I've solved the problem. Look, I also solved the dual problem. So by clearing all the purple entries up here on the primal, I've managed to clear all the purple entries over here on the dual. So I've solved the dual problem. So when we apply the simplex method to the primal problem, which I just illustrated in this particular example, and we can do it both to the two phases with that x0 variable, and we can do the whole thing. We can apply the simplex method to the primal problem in two phases if you didn't start out feasible, and do the analogous pivots on the dual side. When you're done, you will have solved both the primal and the dual problem. Both the primal and the dual problem. And furthermore, you'll have this negative transpose property so that if I have a 5/3 here, I'll have a -5/3 here. But don't forget, but I should point out, this -5/3 is ignoring one important thing. It's ignoring that minus sign right there. So the actual dual has this extra minus sign that my pivot tool doesn't show. I suppose if I were next year, I probably will put a minus sign right there so that the pivot tool shows that the dual is a minus. So anyway, we have this negative transpose property. So whatever there, the negative will be there, but this is the negative of the dual objective. So what does this tell us? Oh, I'm going to get to that later. I forgot my order here. Think about what that tells you. And we'll get back to it. So this suggests another simplex method, the dual simplex method. the dual simplex method is exactly what I just illustrated here. We were doing pivots on a problem that had purple only here and not there. And we ended up going and finding an optimal solution to this problem. So what if our primal problem had purple only here and no purple up there? In my mind, I could think about the dual of that and think about applying the simplex method to it. That's what we want to do here. So the dual simplex method applies when the dual problem is feasible. So that means all the coefficients in the objective have the correct sign, would be negative. But some of the coefficients in the right-hand side will have the wrong sign. And the dual of that problem looks like this. So the coefficients up here have the wrong, some of them have the wrong sign, that's okay, but all these have the right sign. So I can apply the simplex method that I've already shown you to this problem, but do it thinking about it up here. I mean, do the pivots up here instead of down here. So here's a summary of what we do. We choose an index I that's negative, for which bi is negative. The variable yi is the entering variable on the dual side. The variable wi will be the leaving variable on the primal side. We do exactly what we did before. We let that yi increase, holding the other things 0. We figure out which of these z's hit 0 first. Exactly what we've been doing all along. It's just we're doing it on the dual side. And we figure out which of these variables must leave by doing those ratios that I was doing a little mental arithmetic before. So in the dual problem, yi is the entering variable and zj is the leaving variable. But on the primal side, we just do the corresponding pivot where wi is the leaving variable. So the I appeared in the column here, it appears in the row here. This wi is the leaving variable, and xj is the entering variable. And then after the pivot, the primal and the dual are still negative transposes of each other. And so we can continue in this way and improving the dual problem until the dual reaches optimality, and then we've solved the problem. We've solved the primal problem by solving the dual problem. So here's just going through an example. So if we have a primal problem that looks like this, with some negatives, we have the negative transpose of it here. So phi would be the entering variable. And we look down here and we see the 3 and the 2 here. This is on 4 going to array 3, 6. So this z2 is the leaving variable. So the 3 is the pivot element. So the minus 3 would be the pivot element here. I just do that here. So I can do that by looking. I don't even have to write this down, of course, because it's just the negative transpose. I can do this entire thought process here. I look for the most negative. That's the minus 5 here. I look across this row, and in my mind I'm thinking about the dual as I'm looking here and saying, okay, look, on the dual thing there's going to be something starting at 4 going to 0 at a rate of 3. There's something starting at 6 going to 0 at a rate of 2. This is the one that's going to hit first. See, now we're doing those kind of mental ratios, ignoring minus signs, and figuring out which one is the entering variable in this case. And so we have the W2 and the X2 are the give us the pivot. And we do that pivot, it's correct. And I have to do one more pivot, so I pick the minus 6 1/3. I look across here. Let's see, so when it was primal pivots, I was looking for positive numbers in these text fields. Now I'm looking for negative numbers in the text fields, because when I think about the negative transpose, this would be the only candidate, and so x4 must be the entering variable. Yes. Okay, and so I do that pivot. Aha. Okay. Wait, what does it say? That's just summarizing the rule. And so we do that pivot, and we get to here. And now we look at this one, and this variable must be a leaving variable. We look across here for positive numbers. W1 must be the entering variable. And we're optimal. What? Did I say it wrong? Oh, yes, I did say it wrong. My mistake. We're thinking about the duals. We're looking at negative numbers in here, not positive numbers. So I'm looking at these two, doing the mental calculation, 5 at a rate of a half, 2 at a rate of a tenth. I guess this was the one that wins. So it's x1 and x2. So I click on that button to do the pivot around that element, and I end up with an optimal dictionary. So I've just solved a problem that you didn't know an easy way to solve before by thinking about the dual problem. Okay. Those two algorithms by themselves, the primal simplex method, which I showed you first, and the dual simplex method, which I just showed you, are constrained. The primal simplex method only works if you're primal feasible. The dual simplex method only works if you're dual feasible. Here's a problem where I'm primal infeasible and dual infeasible. And by the way, this is yet another version of my little tool here. This version has one extra column here and one extra row here, which is what I'm going to explain right now. So here's a very nice method. Instead of adding that extra x naught variable to the phase 1 problem, let's do a different thing. Let's add a fake objective function, but no new variable, just a fake objective function here. The original right-hand side, a fake objective with all -1s. I'm forcing it to be dual feasible. So if I don't look at the top row and I only look at the second row, my fake objective, I can use the dual simplex method on this to get rid of these purples here and make my thing primal feasible. Once I've done that, I can then ignore I can ignore the fake objective and use the real objective and finish the problem. So this is using the dual simplex method with a fake objective function as a phase 1 method to get all of these having the right sign. And then once these are all the right sign, then I just use the primal simplex method that I showed you at the beginning to finish the problem. So here it is. So for the time being, I'm ignoring the true objective, and I'm doing the dual simplex method. Oh, I already did a pivot. Let me back up here. For the first pivot, I picked the most negative here, which is the -3. I look across here for minus signs. I do ratios. I guess there's a tie here, but I picked W3 and X1 as my first pivot here. So I click on that, and I get to this dictionary. There's a -9 here. And so that will be my leaving variable. I look across here for negative signs. So I have the -6 on a 0. It's going to be a degenerate pivot. And a -1 on a 2. So this is starting at 0, and I have to pick this one. So we're going to do a degenerate pivot. So W2 and X2, I do that pivot. And now I have a -1.5 here. I look across here for negative signs. There's only one of them, so I must pick that one. So I'm going to show that later, I think. I must pick that one, and I do that, and I do that pivot, and now I've gotten rid of all the purples here. So this fake phase 1 problem is optimal. I've solved it to optimality. But it was the fake objective. This wasn't the objective I wanted, but now I'm feasible. So I throw this objective away, and I go back to the original objective. The nice thing about this pivot tool is it's updating the original objective function to keep it up to date using the non-basic variables. So that's our objective function up there. So all I have to do is start looking at that one and ignore the fake one. So that's what I just did here. I just highlighted it differently. And now I look at this and I see it's a little bit hard to read. But is that a 9 there? So x3 is the entering variable. I look down here for, I'm looking for positive entries in this text field. So I guess it's the 1 going at the rate of 2/3. This is going to be the W4 is the one that's going to have to leave. So x3 enters, W4 leaves. I click on that little button there, and I get to here. Now there's only one positive. I look down here to see which one's going to leave. And as I look down here, lo and behold, there's nothing with a strictly positive entry here. None of these variables ever hit 0. This problem is actually primal unbounded. So that's the simplex method. Two-phase, dual for the primal, dual for phase 1, primal for phase 2 version of the simplex method. Okay. Now, so I like that better than the X naught method. I'll give you another version that I also like very much later. Okay, let's go back to the thing I told you to think about, the strong duality theorem. The conclusion on the previous slide is basically what's happening with it, is the essence of the strong duality theorem. If the primal problem has an optimal solution, then the dual problem has an optimal solution, and they're equal to each other. Well, I guess the previous problem was an unbounded one, so that's kind of a special case, but not exactly, because, well, this was actually referring to the one before, I guess. Where was that back here? It was referring to this one. By solving the primal problem, I also solved the dual problem, and the objectives are the same. So there is no duality gap. So to paraphrase, if the primal problem has an optimal solution, there's no duality gap. And the proof is the simplex method. It's an algorithmic proof. The simplex method works. I've told you how to avoid cycling, so you'll never get into an infinite loop. You're always increasing. It doesn't take an infinite number of pivots because there's only a finite number of different dictionaries. So there's not an infinite number of different dictionaries that you could get to. So there's only a finite number. It doesn't cycle. It has to get to the optimal solution. You apply it with the phase 1 and then with the phase 2, you've solved your problem. You look at the dual dictionaries that correspond to all those primal dictionaries, and when you get to the end, you've solved the dual problem. And the objectives are equal. So if the primal problem has an optimal solution, there's no duality gap. Okay. But primal problem doesn't always have an optimal solution. And so in fact, we have to think about some possibilities here. So if the primal problem has an optimal solution, then the dual problem has an optimal solution, and there's no duality gap. If the primal problem is unbounded, because of the weak duality theorem, it tells us that the dual problem must be infeasible. Because if it weren't infeasible, there would be if the primal problem goes all the way forever, continues forever, and if I had some dual value that was here, that would violate the weak duality theorem. I'd have a feasible dual solution that was smaller than a feasible primal solution. So if the primal problem is unbounded, the dual must be infeasible. If the dual problem is unbounded, then by the same argument, the primal problem must be infeasible. So I can have these possibilities, and in all these cases I say there's no gap. There's obviously no gap here, and this is also like no gap. There's sort of no gap and you're sitting out at plus infinity. Here you're sitting at minus infinity and there's no gap. But I haven't ruled out what if the primal problem is infeasible and the dual problem is infeasible. What about that? I haven't said anything that would rule that out. And in fact, that can happen. Here's a simple little example. Let's see. If I negate this second constraint, it becomes x1 minus x2 is greater than or equal to 2. But the first constraint said that the same thing is less than or equal to 1. So that's an infeasible problem. The two constraints contradict each other. Similarly, if I look at the dual, I'm going to have y1 minus y2 is greater or equal to 2. And I'm going to have minus y1 plus y2, minus y2, minus y1 plus y2 is greater or equal to minus 1. Negate that constraint, and it says y1 minus y2 is greater than or equal to, now less than or equal to 1. So both less than or equal to 1 and greater than or equal to 2 can't have both of those. They contradict each other. So this is a simple little 2x2 example where both the primal and the dual are infeasible. And so that's surprising to me. You know, you've got a very elegant theorem, but it's not without, you know, its assumptions. So the assumption is, if the primal problem has an optimal solution, then there's no duality yet. Okay, another important thing to notice, which we'll use later, is this idea of complementary slackness. At optimality, we have complementarity, that the primal variable times the corresponding dual slack is equal to 0, and the dual variable, and the primal slack times the corresponding dual variable is equal to 0. This will be true for all variables. That's true at optimality, no matter what. And the proof is just to really look at the proof of the weak duality theorem all over again and just look at it more carefully here. So again, we start out with the same thing, y transpose ax, but now I'm writing it out in detail. And these are the same steps here, just collecting my sums in different ways. So here I'm doing the sum on I first. But instead of writing the inequality down directly, I'm putting in the slack variable. This is a step that I'm doing a little bit different than I did before. So I just say, look, A transpose Y is equal to C plus Z, so put that in here. But then we know that Z is greater than 0 and xj is greater than 0. All these things are greater than 0. If I just throw these away, I get this inequality. This is really the same thing as before. I'm just writing it with the slacks in there to emphasize how this inequality happens. And on the other side, it's the same kind of thing, but instead of the C plus Z, I get the B minus W. And then I say, well, all the W's and all the Y's are greater than 0, so all these products are greater than 0. This sum that's being subtracted here, if I throw it away, I get something bigger. So that's the whole proof. But by the strong duality theorem, I know that these two things are equal at optimality. And if those things are equal at optimality, then in fact, when I threw things away, I didn't throw anything away. So this sum on J of Zj xj had to be 0. And the sum on I of Wi yi had to be 0. And since all those terms are non-negative, all the terms had to be 0 as well. And so all of those products have to be 0. By the way, that's not only true at optimality, that's also true in every dictionary. Because all I'm using is that my objective functions are equal. But in every pair of dictionaries with the negative transpose property, and remembering that extra minus sign out front, the objective function values are equal in every dictionary pair, primal dual dictionary pair as well. And so we also have complementarity in our dictionaries. And that's a fundamental thing. Okay. But if you're, well, yeah. So maybe just briefly show you, oh, I'm over time. Maybe this is a good point to stop then. So, okay. Any questions for a few minutes, or it's all clear? Yeah.
So for what kind of other classes of optimization problems is there a strong duality theorem?
That's a a good question. Duality theory goes over to convex optimization. But even here, we saw that there is an assumption, and there is a little glitch in that assumption that we can have a duality gap even in linear programming. So you can have duality gaps in every optimization problem, but you do have a duality theory and versions of the strong duality theorem for all of convex optimization. But when you get to non-convex optimization problems, then everything is much harder. So, any other questions? Yeah.
Would the numerical error accumulate as we proceed from not
Absolutely. The question is, does numerical error accumulate? On a computer, whenever you do arithmetic, your errors accumulate. If you're doing floating point or double precision. And so you have to worry about that. And counting number of operations, 10 to the 21st operations is numerical error would really dominate, and you probably wouldn't get the right answer with the Complementary problem. So yes, you want to keep your number of operations small. I have code that I've written for these things, and in double precision, you got about 16 digits in decimal, and so I tend to put in epsilon tolerances that are about 10 to the minus 8 typically, figuring if things got worse than that, then we've done too many arithmetic operations and the problem's just got to go to quad precision basically. So yes, that's always an issue. Yes. Any other questions? Okay, so I will see you later this afternoon.